Welcome to this explainer. Today, we're diving straight into the pure, unfiltered logic that drives exactly how computers solve problems. We're going to map out the foundational architecture of computational thinking and see how it scales all the way from simple decisions to complex data sorting. Think about how you tackle a messy, real-world issue, like, say, navigating city transit during rush hour. You immediately assess your current state, your target destination, and the absolute most efficient path between them. You're deploying logical frameworks instinctively. Let's look at how that natural human instinct translates into rigorous machine logic. Here's our roadmap for today. We'll start with thinking like a computer, move into the anatomy of an algorithm, check out flowcharts and pseudocode, look at testing the logic, and finally, searching and sorting data. Let's get to it.
Section 1. Thinking like a computer.
Before a programmer ever touches a keyboard to write a line of code, they gotta rely on the 4 pillars of computational thinking. First up is decomposition, literally breaking down a massive, intimidating problem into smaller, bite-sized pieces. Then comes abstraction, which is basically filtering out the noise. Next, pattern recognition, looking for similarities with past problems so you aren't just reinventing the wheel. And finally, algorithm design, where you lay out your step-by-step master plan. These 4 techniques together are the ultimate problem-solving toolkit. Now, abstraction is actually really fascinating. It sounds a bit counterintuitive at first, but intentionally ignoring information is one of the most powerful tools you have. By aggressively filtering out irrelevant characteristics and useless details, you drastically speed up your time to a solution. You're just drilling down to the absolute core of the problem.
Moving on to Section 2, Anatomy of an Algorithm. So the crucial takeaway here is that whether you're writing an algorithm to sort a grocery list, calculate an employee's paycheck, or run a complex physics engine, every single algorithm has to share these 5 precise characteristics. They absolutely must have a defined start and stop point, no exceptions. They have to be accurate and unambiguous, because computers only do exactly what you tell them. They need a predefined sequence, they must account for all possible scenarios, and this is a big one, they must be finite. An algorithm that just runs forever without actually finishing its task is a broken algorithm.
Section 3. Flowcharts and pseudocode. Here we have a direct contrast between the 2 most popular planning tools. Flowcharts are fantastic visual blueprints. They use very specific shapes, like ovals for starting and stopping, or diamonds for making decisions. But if your program gets too complex, a flowchart can turn into this messy web of intersecting lines that heavily resist modification. Pseudocode, on the other hand, is text-based. Pseudo literally means imitation. It's an imitation of code written in plain natural language, like English. Because it's just text, it takes way less time to write and is incredibly easy to tweak later as your program evolves. And it's honestly kind of mind-blowing to realize that just 3 basic logic structures are totally sufficient for writing absolutely any computer program in existence. Sequence just means doing things in order. Selection means making decisions, like an if-then statement. And iteration means repeating an action using a loop until a specific condition is met. Master those 3, and you can build practically anything. All right, Section 4, Testing the Logic. This brings us to a manual testing method called a dry run using a trace table. And there's actually no computer involved here at all, just a programmer, a pen, and some paper. You set up a table with all your variables like total, count, and number. Then you manually step through every single line of your algorithm. Whenever a variable changes, you write down the new value. If the final output on your paper doesn't match what you originally expected, like expecting a total of 21 but getting something else entirely, the trace table lets you spot the exact line of instruction where that logic error occurred. Finally, Section 5, Searching and Sorting Data. When it comes to searching, we usually look at 2 main methods: linear search and binary search. A linear search is super simple. It checks the first item, then the second, then the third until it finds a match. It works perfectly fine on unsorted data, but man, it is slow. So where would we actually prefer a binary search over a linear search? The answer is large data sets. Binary search is a brilliant divide-and-conquer technique that recursively halves the searchable items, making it insanely efficient. But there is a catch. For a binary search to actually work, the data has to already be sorted. Let's visualize this binary search in action. Imagine we have a sorted array of numbers, and we're hunting for the target number 31. Right off the bat, the algorithm calculates the exact midpoint of our array. In this case, it checks the middle position and finds the number 27. Now the computer asks, is our target 31
greater than or less than 27. Well, it's higher, so we instantly know it cannot be in the lower half of the list. We completely throw out that lower half, saving massive amounts of time. The algorithm then shifts its focus to the upper portion, recalculates the center, and finds a brand new midpoint, which is 33. The algorithm asks one more time, is 31 greater or less than 33? It's less, so it discards the upper half, slices the remaining piece one more time, and boom, it instantly lands on our target 31. It's such a great illustration of how the divide and conquer technique drastically cuts down the number of comparisons compared to just checking every single box one by one.
But remember, binary search only works if the data is already organized. Just as searching requires strategy, organizing data relies heavily on sorting algorithms. Two foundational ones are bubble sort and insertion sort. Bubble sort is simple but a bit clunky. It steps through the list, compares adjacent elements, and repeatedly swaps them if they're in the wrong order. It gets the job done, sure, but it's generally pretty slow because it requires so many swaps. Insertion sort, however, takes a totally different approach. It builds a final sorted array, one single element at a time, picking up an item and inserting it exactly where it belongs among the previously sorted items. Because it involves fewer swaps, it's generally a much faster, more elegant solution.
We've covered a ton of ground today, from abstracting away the noise to dividing and conquering complex data sets. But here is the ultimate takeaway. As our world generates exponentially more data every single day, these foundational algorithms are literally the only thing keeping our digital universe from collapsing into total chaos. It kind of makes you wonder, right? As artificial intelligence begins writing its own algorithms, will it stick to these human-made pillars of computational thinking, or will it invent a totally new logic that we can't even comprehend?